Conference, Unified Field Mechanics 2, and the second subtitle is empirical tests, so I at least thought at least someone should give lip service to that. So in view of Daniel not being here, and I don't want to call my talk impromptu exactly, but since my computer is still at Orly for a couple more days, it will be an interesting challenge. Questions at the end, but I seem to be notorious for using terms that people don't understand fully easily. So if you have a question about a term, please interrupt in transit. Classical mechanics, quantum mechanics. We haven't had an age of discovery for 100 years. The next age of discovery is upon us. That'll be unified field mechanics, which I've coined. Maybe the physics community has a slightly different. But it seems like their completion of the standard model isn't yet to go beyond 4 dimensions. So we had the Rayleigh gene, infinities in the Rayleigh genes law pointed the way to the discovery of quantum mechanics. Right now the infinities in renormalization are pointing the way to the next age of discovery. Almost all physicists believe that quantum mechanics is the basement of reality. If there are additional dimensions, since we don't see them, they're curled up microscopically at the Planck scale, and as you can see, that's still part of the standard model. But there's an alternative interpretation for large-scale. Nima Arkani Hamid talks about dimensions of 1 millimeter or so. I'm more in line with Lisa Randall of Harvard, who suggests infinite-sized additional dimensionality. CERN has proposed attempts at experiment, but as you know, following that, you know that they've recently discovered pentaquarks and things, but the additional dimensionalities may take more energy. The model I will present, when it is proven, if it's not falsified, will put an end to the need for an accelerator because it will allow tabletop low energy experiments. It'll be a different type of cross-section. That's one of the points I hope to get across to you in some semblance of understandability. As pretty much everyone in this room, I believe, knows, the quantum uncertainty principle is sacrosanct. It's been empirically demonstrated, especially in terms of the Copenhagen interpretation. And so how, but of course Copenhagen is in Minkowski, Riemann, Euclidean space, so the simple answer is to do something else that carries us beyond the limits of space that the quantum theory is embraced in.
Can I ask one question?
That was one, so you mean you want to ask two? I'm sorry. We're physicists, we want precise rigor, and I'm saying that because you can pick on me all you want. Go ahead.
It's one question with many parts.
Not exactly.
The word dimension is often used, and I believe, in very different contexts. The dimension that I like to use is the three-dimensional world that I see, which can be very parameterized by a set of arrays, physical arrays. When you start going to other dimensions, even 6 dimensions, you start talking about abstract parameters where each parameter now becomes a dimension. Or a field.
Yes, they don't have to all be top temporal or spatial, like we can call them degrees of freedom. I'm going to say part of your view is myopic, but in physics, unless there's an experiment, we don't accept the theory until there's an experiment. But we do have string theory that proposes additional dimensionality or degrees of freedom. Peter has done well in talking about, when he talks about, as you saw from his talk, charge and mass, and those aren't dimensions of space-time, which we usually consider dimensions, but additional parameters or degrees of freedom. So a dimension can also be synonymous with a degree of freedom. I won't have much time maybe today, but
that's what I'm asking. So the word dimension in your case is...
I'm using it in degree as degrees of freedom, but I didn't want to start by saying that.
You couldn't have more spatial dimensions than we have in the ordinary sense, because mathematics doesn't allow it, except you could have Octonian dimensions. So if you went beyond that, there's no mathematics that can do
What do
it.
you mean? Mathematics allows you to have...
No, but it doesn't. No, it doesn't allow you to have dimensions of space as we have them and extend those, because those dimensions.
I think, excuse me, you're saying you want to have algebraic spaces that have...
Yeah, if we have space as we now know it, we can't just extend that to any number of dimensions, because it wouldn't be a space as we know it.
I think the key is now knowing.
The as we know it, like, what is the meaning of is?
No. I mean, we couldn't have a cross product.
I won't talk to you about it now, it will go on forever.
Yeah. We can't have it.
And I'm not going to argue with that, as Peter has been so apt to describe for probably most of his whole career about the fermionic vertex being a quaternion, and when you add the anti-space, you get the nilpotency. There need be no argument for that. That's the foundation of what I want, where I want to take this. And I think I first learned the term from Peter of complex quaternion algebra. But what I need is a complex quaternion Clifford algebra, because and I'm going to, I think Jose's not here tomorrow, I'm going to go spend 10 days in Romania for a workshop, summer school on Clifford algebra. With Clifford algebra, you can have a 3 or 4 dimensional or whatever dimensional subspace you want, and then you can build another manifold or space on top of that. String theory does talk about a dual 3 torus or a 6-dimensional Calabi-Yau mirror symmetric space, and some of those they consider as spatial. I am in my model considering some of them as spatial, but there are, and I just come to the realization, this is kind of a segue. When I just finished a book on quantum computing, it's being typeset. It was well beyond me, and so I had to do like 3 times as much research to write that book as I normally would. It's my 30th book. I discovered in Googling around for terms a thing called I can't remember the name of it, the something snowflake, based on the Fano plane of quaternions. I don't think I can draw it. I'll try a little bit. Each corner of this object had, it's like a quaternion vertex, and I've got this, I'll have to wait, but it would enfold into the Fano plane. I'm probably not even going to be able to draw this. It's a triangular structure. If you can Google the Fano plane, you get or Google images, and you get but the beauty of this, I need all right, let me try again, something else. So here's the quantum particle in the box in free space or Minkowski space if you want to add it. This has been the basis of reality and the fermionic vertex for a long time. So I'm going to keep it 2-dimensional to simplify it. So let's add Peter's space, anti-space. Only I should have made these crossovers. So that's the first doubling, and don't forget that Bruce's. It's not about, at this moment, the dimensionality, but in topology, Lou talks about this particle in free space as a Notch shadow. So that shadow, it's locked, that's the uncertainty principle. You get up in the first doubling of the first topological raise into this higher dimensional space, and these things are not the reduced knots, but they're able to have crossovers. So it gets complex as we go up the scale, because then these things have to undergo other doublings. A point which is a little bit out of order, which I realized I never had, mostly following Peter's lead, any interest in the octonions. But, because Hamilton had to sacrifice commutativity, and the Artonians lose a lot more of the things associated with algebra, but all I need to use the Artonians for in this higher dimensional space is to run these crossovers so that, okay, now back again. In order to, you can find it online easily, some documents on how to, simple methods to surmount the uncertainty principle. Once you add more degrees of freedom, but if I'm going to build it on quaternions, which is simple, I have to break Hamilton's closure. As you know, if you know the history of quaternions, that looks more like a J, okay. That still looks more like a J, but that's an I and that's a J. When Hamilton first added the J, it didn't work. It was only when he added the K that the quaternion algebra had closure and it was a complete algebra. I can't get out of the space of the standard model with this closure. I need to break the closure. In terms of, this is the reason I was teasing Lou about, I want to add topology and knot theory to his I block. And because to build up the algebra to do this, and this leads in, that's what I was going to say a few paragraphs back about the Bohm interpretation, a continuous evolution without collapse of the wave function, and one of the interpretations is annihilation, creation, you get a continuous wave based on annihilation and creation vectors. So as you all know, Bohm's interpretation and Cramer's transactional interpretation have been marginalized because they're not considered to add any new information. And Cramer's sounds, in a sense, silly in some ways, that the present instant is a standing wave of the future past. Present past, they're going to be saying. And he calls that a standing wave. But, most people say, well, a standing wave in a string, yeah, that's too simple. But if you have a hyperspherical standing wave, like you apply it to the Calabi-Yau mirror symmetric dual torus, then you can also take Cramer and Bohm and complete them in a higher dimensional space. So the reason you want to do that is, if this is what we call the basement of reality right now, all contemporary physicists essentially, and we can't get beyond that, but extending Bohm and Cramer to higher dimensions, and then we're going to build that, maybe not today, we won't get to it, on the Calabi-Yau mirror symmetry. And when you use that 6-dimensional space, that gets double to get into a 12-dimensional space, and then you don't think about this space as the observer. That's because then you have too many dimensions. So you switch your observation to here, but that's another philosophical issue. So below this, it's like the line element. We have a beat frequency of this structure, and as it's built up, let me see if I can draw something like this. Uncertainty becomes a manifold of finite dimensionality. So at first I thought maybe it was a 3-dimensional manifold, but I've now realized as I've tried to study the topology and stuff that it's with building on Peter's space anti-space and the Calabi-Yau mirror symmetric duality. So the point is, in the experiment, I'm going to skip around as without my notes to keep me ordered. I'm a little bit, I'm loony anyway, but this is what you get. If this is 3-space, for the last 100 to 200 years, all the spectrometry has been done in 3-space. So this would be the lowest Bohr orbit is right in here. I was a little bit ticked at Vigier for the 2000 conference in Berkeley because I've gone back to Paris 3 or 4 times, and we're going to work on a paper on the integration or the redshift and quantum and the background radiation as I forget the rest of it. And instead, just like the day I left, he got a paper from his colleagues in Yugoslavia, Maric and Drakic, about tight-bound states in hydrogen, and them explaining cold fusion. To anybody, how can there be more orbits below the lowest Bohr orbit? You know, in a tight-bound state, it didn't make any sense. So as a puerile little baby boy, I ignored that paper for 12 years. And then in that 12 years, I worked on my cosmology that had all of this. And then when I read it, I realized, and this became a big key. Some of you may have seen the simple equation from about 1895, the volume of hyperspheres. Calculate the volume of hyperspheres. So if this is 3 space, 4 space, 5 space, you can calculate these additional volumes. So, all right, so the point I want to make here is, like a holophone or lighthouse, we don't see this because of the knot. We're locked in by the uncertainty principle. One of my major premises is, beneath this, or however you want to say it, there's this new beat frequency, higher dimensional beat frequency of space-time. So the lock of the uncertainty principle opens, closes, and we don't see it because in 4-dimensional measurements, you touch an object, and the more you accurately measure this one, the less accurate that one. I mean, we're locked into 3 or 4 space by the uncertainty principle. So how do you get beyond this? You Dirac covariant polarized vacuum extended electromagnetic theory, popular 100 years ago maybe, but it was perceived that it conflicts with gauge theory. Gauge theory is so popular that that was enough to throw it out, especially since the Proco equation, maybe you've heard of that, Einstein, Schrodinger, Vigier, and many others postulated a minute photon mass. And the centrum of the wave, they did a mass which is 10 to the minus 62. I changed that a little bit, that the mass only occurred at the centrum when there was a coupling to the vacuum, so you get a little internal motion. This has also been abandoned because of, and Peter talks about no need for extended particles, but if you go into a higher space, there is this. So it's massless during propagation, but then it couples to the vacuum and over cosmological distance. So when Hubble discovered redshift, not an expansion of the universe, so this is the tired light model, you get attenuation to invisibility of redshift with small photon mass. So physics threw that out. They didn't like that. So, but the Dirac covariant polarized vacuum, the best indicia that it exists is the Casimir effect. You can't really explain the Casimir effect very well without a Dirac polarized vacuum. The Zeeman effect, the Aharonov-Bohm effect are all lesser indicias of a Dirac polarized vacuum. So, through a resonance, you have to kind of figure out what this beat frequency is, or if there's a nilpotent way, you can set up the beat frequency by the way you set up your resonance hierarchy. And back to Dubois for a minute, who I'm taking over, he talked about an incursive oscillator. So you have a regular harmonic wave, but if you have an incursive oscillator, you can get a delta t. And the delta t, you can arbitrarily choose to be the size of the hole you want to punch in space-time. So,
is t mean time here?
yes, but just in the equations of harmonic oscillators, not the kind of time we want to time. So you open your hole in this beat frequency in terms of this. So remember the volume of hyperspheres. So there's a little addition. So here's the nucleus. Here's the first Bohr orbit, a half an angstrom. And the next one is 2 angstroms approximately. So with using this hyperspherical equation, you can calculate an approximation to predict 2 or 3 additional Bohr spectrums in this gap between here. But they're not in between here. When this opens, you have another, here's the usual 3-dimensional cavity, here's another cavity. So you're going to get a delta, a change in this radius. So that's your first additional Bohr orbit. And then you do, then if you're successful, you do another one. And that one's a little harder because you're going to need to add some kind of a Bessel function or something and be very careful, or you're going to collapse this into the uncertainty principle. So now you hopefully all know from high school chemistry, the excited electron in a hydrogen atom, when it has enough energy, it flies off to infinity. So I think 5 dimensions is maybe too simple, so it's not going to happen, but it could. The theory isn't developed enough to be positive, but it could fly off to infinity at the 3rd hyperspherical dimension. Then you're going to get your signal back. This is your first signal back, your second signal. Your 3rd signal will either come back or it will fly off to infinity and you won't get any signal back. But if this manifold and its mirror symmetry insist on to be a true dual Calabi-Yau 3 torus, then it won't be until after the 5th dimension that the signal flies off to infinity. So now we have a way to surmount the uncertainty principle beyond this manifold of uncertainty, and we will then have access to the higher dimensional realm of unified field mechanics. This experiment is almost like the discovery of electricity. The same method you use to get these other dimensions, you just change it a little bit. In a sense, as part of like a change of phase. Then there's all kinds of other things you can do with this. And then one of the next, I'm very interested in this in terms of quantum computing. This is my 3D quantum particle in a box. The mirror image of the mirror image is causally free. It takes 12 dimensions, it seems to do that. So, and I wanted to do something else first before that. There's brain topological structure. This is again back to the mirror symmetry. So the lowest one that's ready to collapse into the singularity, the fermionic singularity, is not quite as complex because it's in lower space. But as you approach, there's more and more doublings. So you need more and more components. So I don't know how to draw it, but this gets more complex. And that's why you actually then need the complex quaternion Clifford algebra. And this is where, when you get these higher topological aspects, that their job is only to run the crossovers and under crossovers so that you can break Hamilton's closure and open it again to allow access, experimental access to the dimensions beyond it. And I'm claiming, I'm not making this up, but this is the actual basis of reality. This is what reality is. Matter is no longer this vertex, this singularity, 0-dimensional or 3-dimensional quaternion vertex. Matter is now a 12-dimensional or 12 degrees of freedom object. That is very important to realize this. This is marvelous. So we're going to have access to all this. So back to quantum computing. So this quantum particle in the box in 3 space or 4 space if you want. This is cycling. This is a scale invariant cycling through all of this, and its cycling is back to Bohm's and Kramer's annihilation, creation, annihilation. The ontological, this is not a phenomenological way anymore, but it's an ontological interpretation of it. Segue again for a moment. The unified field does not provide a 5th force, it provides a force of coherence. So for us in time, or 3 space, the railroad tracks recede. In order to open this gate and close this gate, the unified field, when it's applied periodically, it's a force of coherence, and it parallels these vertices again, and allows, I don't have time to get into consciousness, but when that gate is open, that's when the élan vital, or life principle, comes in to animate biology. About Descartes. Descartes has, when they used to say when Eccles was alive, how can you argue with a Nobel Prize winner, Brian? You know, how can you insult a Nobel Prize winner? As soon as Eccles died, Cartesian interactive dualism was moronic and ancient, and forget about it. So if you're a Cartesian dualist right now, you're going to have to do something like that. But they, as we do in physics, Descartes said his res cogitans was immaterial. Not non-physical, immaterial. You go get out your Webster's, one of the definitions of immaterial is spiritual. And as you may, if you know your history, Descartes said he got this as a revelation from God. You don't have to wax theological, you can say this is a new physical action principle of the unified field. But anyway, we now have, in unified field mechanics, the next generation of physics, not only access to this higher dimensional realm and a new different, so you're going to just do a cross section as these things are collapsing down into the free space. You do a different kind of cross section, and you can actually see inside matter much more clearly without having to smash things and look at particle spreads. This will be a different kind of cross section to see the inside and the structure of these this higher dimensional brain dynamics. This Necker cube or ambiguous cube. Familiar with that? You look at a, probably can't even draw a cube. You look at the vertices of a Necker ambiguous cube, they switch. It's called, Toffoli called it topological switching. There's no energy exchange. So this is the basis for mind-body interaction. And you know, it's not a monism, you have a dualism between these two things. So there'll be consciousness-based technologies, no need for particle accelerators. There'll be, I'll segue into this one. So I filed a patent on quantum computing, but I let it go after it was published and then fight the rest of the way because if you know anything about patent law, an expert in the field must technically or theoretically be able to build your model. Well, there isn't any expert in the field. I'm not even an expert in the field, so I didn't want to fight with them any longer because I didn't think it was. I might have somehow been able to do it by changing the wording, but so I let that go. But it's published. But anyway, that's so it'll be a while before there's an expert in that field. The one of the leading models of quantum computing is the quantum Hall, what's it called? The
topological quantum computer.
Yeah, and the Annion braid. And the beauty theoretically, and there's no evidence for it, of the Annion braid is it's inaccessible. It's inaccessible to experiment, but because it's locked behind reality, it doesn't decohere. So it's really one of the only models besides mine that thinks that they've got a handle, because that's called the last remaining hurdle to quantum computing is decoherence. So with my model, if they wanted to just as a proof of concept, they could, you know, it's at absolute zero in quantum Hall semiconductors. I think some of them may even be using Joseph's injunctions or something like that. But so in the last weeks of my writing my quantum computing book, you know, I was climbing the ladder of theories of physics. You know, classical field theory, quantum field theory, relativistic quantum field theory. And I didn't like the idea, didn't feel that there should be a relativistic topological quantum field theory, but Lou said it wasn't, you could have one if I wanted, but I think we also are going to go beyond relativistic models. And if you want to look at the amplituhedron that Nima Akarni-Hammond talks about, segue again, quantum theory is based on locality, and unitarity. With the amplitude, which can take 10,000 Feynman diagrams into one geometric structure, he actually talks about going beyond unitarity and locality. When I was at Boston University in 1996, PhysComp 96, Tom Toffoli, some of you have heard of him, one of the Toffoli gate, very big in quantum computing. So I was standing here, Tom was there, and a Russian postdoc was there, and he postulated a relativistic qubit. Toffoli called himself, you can't do that, you can't do that for no reason. Of course, I always thought that that's really a reason to work on things in physics or science. But I went and interviewed him a little bit, and I wrote it down, and I used that because it gives an additional degree of freedom. And so I've been slowly developing that in my quantum computing models. And so when I was writing the book, I found that there was a very new field of relativistic information processing, and one of them also mentioned a relativistic qubit. So I emailed Blasov and said, well, it took 20 years, but just a couple of years ago, he sent me an email of a paper that I'd missed that was just before that. So 20 years later, now it's finally, but my model also goes along beyond that. And as those who follow quantum computing, you may know that they want to have exponential and logarithmic or whatever kind of algorithmic speedups. Well, once I've started developing the topological phase, ontological phase, topological field theory, I was able to postulate an instantaneous algorithm in terms of Nema's amplitude-hadron. And if that sounds preposterous, if you understand the EPR experiment sufficiently well, it's not a faster than light, it's an instantaneous connection in a holographic or non-local background. So eventually we'll probably end up having a type of quantum algorithm that is instantaneous. This is, I think I've gone to different places than, let's see, I think I promised, maybe it was Wolfgang about talking, no, it was, where is he hiding? One of our Italian, that I would spend a lot more time talking about the experiment. Let's see. How much time will I have left?
Half an hour.
Okay.
25 minutes.
And maybe we should, if I give up 10 minutes, then Dionysius could finish his talk also. If we want to squeeze that in today, you think? Or?
Yes.
Okay, that's a good vote. One vote over many. That's, we put with the lost sheep or whatever we choose here. So help me to finish 10 minutes early, and I suppose we'll have to put him in maybe just before the end and not interrupt the rest of the people's time.
It's 3:30.
Okay. Let me pause for a minute, see if I can collect my thought. So I'm really a little bambino about, my mental age about 11. So when I lost my computer, I wasn't going to immediately jump off the bridge, but I wanted to lose weight, go home to America having lost weight. So the first thing I did is I went to the breakfast and had about 5 breakfasts, because it commits slow suicide. I can justify that and maybe not offend God too much, because anyway. So now that I found my computer, it's a hard adjustment to switch back from suicide to I should live long enough to complete my work. All right. NIST, the National Institute of Standards and Technology, they have all the equipment. And there was just, I think it's on the Baltimore website. I think it says either colloquium or there's some place that has a memory stick thing. There's a lot of some books and papers that surround this experimental work. One of them is by an Australian called Chandler. He did 10 years of work on hydrogen trying to violate QED. And he found a violation, but it wasn't in physics. If you don't get it above the sigma 5, it's not considered enough to get excited about. These were below the sigma 5. So in 2012, he decided instead take a titanium atom and strip off all the electrons but one. So in a sense, he had a huge hydrogen-like atom. He got a statistical violation of QED at the sigma 5, so people are starting to talk, whispering about Nobel Prize or something, but QED, one of the most perfect, Feynman and others say, you know, QED is one of the most perfect and best theories we've ever had. So now, this is another indicia that we're about to go beyond the standard model. So, we can try to make enough sense of the way I mean, last year, the year before, Lou argued with me for about 8 months about what I said meant by a manifold, and I didn't know exactly yet what kind of manifold I wanted to use because I was still developing the theory. So it was humorous to me, I'm not sure about Lou, but after 8 months he goes, oh, you just mean manifold in general, so it's okay. Maybe I'd forgotten that, but anyway, so, and Peter involved me out, Luke involved me out, but if we try to design the experiment, couching it in Kaluza-Klein theory, it's a legitimate way to approach a model. So we're going to say we want to improve Chandler's experiment and discuss it in terms of, because Chandler didn't go into extra dimensions or anything like that, or degrees of freedom. So we want to improve Chandler's experiment in terms of Kaluza-Klein theory. We can probably write an experiment that is acceptable to NIST. They're very busy. It'll take us a year to, you know, I don't have anything to pay these guys, so I can only insult them or try to buy them lunch or something, you know, I don't know. But if anybody else wants to help, if you go read about this, you know, nobody cares. You know, this is a big deal if it works. Get in their queue. It'll take a year to write the paper if we start now, a year to get in their queue, and then another year. So 3 years away. From 3 years from now, we can have that experiment. Getting into the first additional dimension, this is the free space cavity, that will found unified field mechanics. But to run the quantum computer, once we can do the rest of that, I can virtually guarantee a quantum computer that there's, you know, the rest of the community perhaps doesn't agree, but they're still stuck. Every 100, 200 ways of trying to implement quantum computing, it's all stuck in the uncertainty principle. So this violates the uncertainty principle, so you can virtually guarantee the building of a quantum computer, and so we can have that as soon as we get to where it flies off to infinity, then immediately take your substrate that you've been working on, you have a viable bulk quantum computer. So it could be just 3 or 4 years away, or if this is more difficult. But by then a lot of people, people will jump on, will get enough intelligence to the subtleties of how to have this resonance hierarchy coupled with the Bessel function and Dubois and cursive oscillator and the hyperspherical volume equations, and we'll understand that manifold well enough to do the resonance hierarchy subtly enough that it won't collapse into itself if we have it off a little bit, because it'll getting the deeper, to get into the last cavity where you fly up to infinity, the experiment will have to be more and more precise. But anyway, try to capture the vision of this. I won't tell you how I figured it out, because, you know, some of you will be, you know, I think I stole it from some Neptunian or something. But anyway, it's experimentally testable, so that makes it worth more than if it was just, I went to Singapore to Yang Mills 60, and I was very proud of myself that, let's see, who was it? David Gross. I have his quote on videotape, "Some crazy experiment." So I can tell you right off it's some crazy experiment, but if it wasn't a crazy experiment, it wouldn't be worth trying, right? Isn't every new thing kind of crazy? I mean, let me try to talk about something that's more important.
Is there any description of tangible equipment that you need for this experiment?
Yeah, so read Chandler's experiment and the equipment he's got, that's what it is. NIST has all the resonance and associated electronic equipment for a hydrogen cavity that, instead of doing it the way that Chandler did, we're going to apply this higher dimensional, non-local beat frequency resonance hierarchy instead. So, you know, there'll probably be a little grant money for scientists, but NIST has all the equipment. So that part's really cheap. I think if you type in Google Amoroso,
hydrogen and you oscillate it with some, I mean, what are you thinking?
matter,
Or does anybody else know this?
nobody knows. I'm making it up with cerebral diarrhea as I go along. Matter is no longer this fermionic singularity. If you want to do this experiment, this higher dimensional, at least it's a dual three torus, but it's doubled. So there's a 12-dimensional object. Matter is now a 12-dimensional object. You have to get that. You have to get that. And we don't want to think about this in terms of what you say. I only know the free space I see. Well, you've got to forget about that and uncouple from this and think about it in terms of this. There's times when you want to think about that, but for this matter is now this topological object, these double, and it looks like the next age of discovery will be topological and knot theory. That seems clear, because even string theory is already there, all these brains. This is all about their brains in the 5 models of string theory.
Yeah, but what I'm asking is, you're saying, you're talking about an experiment, you're talking about taking it a year and so on and so forth. What equipment, you know, are you going to take a hydrogen atom that's...
NIST, read Chandler's paper, it's online, and it's a nice, beautiful paper. They describe the experiment at NIST. NIST has this hydrogen chamber, and all the apparatus to read it and energize it, and you know, it's going to be quicker than I can, so that's there. So we're going to do this direct polarized vacuum, Signac effect, and cursive oscillator resonance hierarchy to send a signal timed to go through the higher dimensional hyperspace, higher dimensional. Here's regular free space. We've done all of our spectral work. When this is opened into the next cavity, there's going to be a signal coming back, which is another hidden line in hydrogen. Below is an oxymoron. Until you open into a higher dimensional space, then it's going to be here between the half angstrom and 2 angstrom second orbit of the electron. And this can
you're going to take Chandler's equipment, you're going to change it.
Not taking Chandler's equipment, not taking NIST's equipment.
And this equipment,
Yes.
you're going to modify it or change something about it so it's a different...
I'm not going to modify it, I'm going to use it differently. Chandler,
Okay, how are you going to use it differently? What are you going to do? What do you want it to do?
take an electromagnetic resonance hierarchy and apply it to hydrogen, timed when this cavity is open.
Where do you buy a generator for this hierarchy?
NIST has all the equipment. I need an RF generator that will
RF is
work
in
on
free
the
space.
polarized direct vacuum.
The RF doesn't have any hierarchy to it. It's in free space. I used to have it.
After all I've said, you still want to stay in 3 space? I just talked about an system on a 12 space. Coming out of kindergarten.
I don't have one.
Keep it.
I can't. I'm going to be Feynman on this one. I'm going to be like Richard Feynman on this one. I'm tired of trying to sell this for all these years and not one person gets one bit of it because they don't want to go beyond 3 space. They don't like string theory. They don't like topology. It's simplistically, I take a Dirac polarized vacuum, which no physicist believes exists. I run a Dubois in cursive Signac effect resonating oscillator, timed when this opens with this beat frequency, which you calculate, which according to my model of de Bohm and Kramer, we don't see it because we're in 3 space with the uncertainty principle. This is not an experiment made up, this is reality. Behind what we don't see in reality, this opens and closes. This is another part of Peter's nilpotent hierarchy. Nilpotency for Peter, he still got it as space anti-space. I just built on it up to 12 dimensions. Nothing new, nothing there. So start with the simplistic little pieces of it and try to grasp each one as you want to go along. It's a paradigm shift, so it's full of, you know.
Yes, but imagine I'm in this person. You're asking me to do something with my hands. Here's a piece of equipment. Here I've got what I think that's here to say is I'm going to add a frequency.
The proposal yet.
Okay.
We have to write the proposal. We're going to improve Chandler's experiment in terms of a Kaluza-Klein instead of the way Chandler did it. And we're going to do it with the resonance hierarchy on hydrogen. You know, I can't go for hours anymore beyond those things at the moment because each one of those is going to take half an hour to pick on each one of them. But just get the framework. I want you to get the framework. QC is not the basement of reality. In improving de Broglie, Bohm, and Kramer, we have a structure, a higher dimensional brain structure, that creates components to this shadow of a quantum particle in the box in 3 space, but it's instead, matter is this higher dimensional structure of brains that, in string theory, they already have that. The problem with string theory is they want one single compactification. In this model, compactification goes 12, 11, 10, 10, you know, it cycles so that the cavity can open. Planck is no longer Planck, there's a virtual Planck that cycles from virtual Plancks to the more radius of the hydrogen atom. In the original hadronic form of string theory, they had a tachyon, so they threw it out because they thought that was non-physical. But apply that to Kramer, you have a virtual tachyon-tardon interaction that build this up. They also had didn't like for some reason, a variable string tension. So they threw that out. The original hadronic form had a variable string tension. The variable string tension in these cyclings also works perfectly, but you know, that's a 500-page book. I don't want to write I'm not capable, I don't want to write the 500-page book at this time, but you know, because all this stuff is in string theory. I could talk about this in terms of string theory.
I'm not asking about theory, I'm asking about is this frequency stuff you're talking about, is it going to be an electromagnetic frequency so I can buy an electromagnetic frequency generator and add it to the equipment that I have? If I'm in this representative, I'm asking, what do I do to implement your experiment?
I didn't submit the experimental design to you yet, so you do nothing until we write it. And I don't care about that. I want to tell you what I want to do. How can you worry about that before you get any of this? Do you believe that a singularity is now this structure? Do you believe that quantum mechanics isn't the basement, that there's an underlying beat frequency? Do you believe any of this other stuff? You got to get all of that way before that, and it may be that we don't mention any of that. We're going to just stick with Kaluza-Klein theory, NIST, and not tell anybody any of this, so that we don't get up against any of this. Go ahead, Ferrasi. Oh, it's done. Too late. Too late. Don't, what do they call it? Not flatter. Don't patronize me with your fake applause. Anyway, there's not enough air conditioning in this room. And I'm Italian. I can't help but be excited about my own work. Einstein was a genius. He was not wrong about everything.
Except the wrong one.
Except the wrong one.
Well, we could take a break for 10 minutes.
No time.
I suggest we take a break for 10 minutes.
No, you have, I think we don't want to break the other schedule yet, so we'll stick you with
That'll take us
it.
to 3:40, start at 3:40. That puts us right on the schedule.
What about a coffee break? Don't you want to wait till the coffee break?
Well, I don't know. I think we aren't ready for a coffee break yet.
Well, we didn't just have to pretend I didn't talk and just go on to the next thing more
The
relaxed.
next talk is 3:40 to 4:20, and then it's a coffee break.
Well, that puts us 10 minutes ahead, which is what we want, so just invite the next speaker up, please.
You want the next speaker right
Yes,
now?
Fabio.
Fabio?
Cantone.
You expect it.
Okay.